Welcome back to Mining of Massive Datasets. In today's lecture, we're going to look at a new topic, online algorithms. And we're going to look at a particular application of online algorithms, which is performance-based advertising, the kind of advertising that you see on the web or on mobile. Now, in the classic model of algorithms, which we're all familiar with, you get to see the entire input, and then you compute some function of it. For example, you might be given a set of data points, and you might want to compute clusters on those data points. In this context, we call the classic model of algorithms an offline algorithm. An offline algorithm has access to its entire input data set. The kind of algorithms that we're going to look at in today's lecture, called online algorithms, don't get to see the entire data set at one time. They get to see the input one piece at a time. They don't see all the input. And yet, as they see a partial input, they have to make some kind of irrevocable decision along the way. They produce part of their output, even when they've seen only a part of the input. And this is kind of similar to the data stream model, but it's not identical. There are certain subtle differences that will become apparent as we go along. We're going to start our discussion of online algorithms by looking at a very simple problem called bipartite matching. So the bipartite matching problem starts with a bipartite graph. So here we have a bipartite graph with two sets of nodes or vertices. We've labeled one set of nodes boys and the other set of nodes girls. We could have equally well labeled them something else, but it just so happens to be convenient to label them boys and girls in this context. And in this case, let's say the edges between the vertices signify compatibility between boys and girls, right? And the goal of the bipartite matching problem is to match as many compatible pairs of boys and girls as possible. That is, find as many pairs of nodes as possible, subject to the constraint that those pairs of nodes are connected by an edge. For example, here we've found three pairs of nodes, 1A, 2B, and 3D. And in each case, this is a compatible pair. There is an edge between each pair of nodes that we've picked. And notice that once we've picked 1A, 2B, and 3D, we are unable to do anything with boy 4 or girl C because there is no edge between them, and there are no other boys or girls that are available. The only edge that boy 4 has is to girl A, but girl A is already paired with boy 1, so you can't pair them up. So in this case, we produced matching of cardinality 3 because we've found three pairs that we could match up. So in the cardinality of the matching in this case is 3. Now, with the same graph, it turns out that we can actually do better. We can find a matching of cardinality 4 if we are a little bit more clever. And here is an example of a matching of cardinality 4. We've matched 1C, 2B, 3D, and 4A. And once we do that, we matched every boy with some girl and every girl with some boy. And this is what's called a perfect matching because it matches every node to some other node in the graph. To clarify our terminology, perfect matching is a matching that matches every vertex in the graph or every node in the graph. And a maximum matching is a matching that is as large as possible for the given graph. For example, in this case, the matching M is both a perfect matching and a maximum matching. Every perfect matching has to be maximum because you can't obviously find a matching that's larger than perfect. However, there could be graphs where there is no perfect matching, but there's always a maximum matching, which is the best that you can do for that given graph. So in this case, the maximum matching has cardinality 4, whereas the earlier matching that we found had just cardinality 3 and is not a maximum matching. Now, the goal of the bipartite matching problem is to find the maximum matching or find a maximum matching, since the maximum matching is not necessarily unique. The goal is to find a maximum matching for a given bipartite graph, And if the maximum matching happens to be a perfect one, we'll end up finding a perfect one. If not, it'll just be a maximum matching. Now, the matching problem is a well-studied problem in the field of algorithms, there is a very well-known and elegant polynomial time offline algorithm. Remember, an offline algorithm is when you have the entire graph available to the algorithm. And it's based on this idea of augmenting paths. It's a very classic algorithm from 1973 by Hopcroft and Karp. If you're curious, you can look it up on Wikipedia following that the link that I've given there. Now, however, suppose you don't know the entire graph in advance. You only have a piece of the graph available to you at any point. In the online version of the graph matching problem, we're initially given the sets boys and girls, the two sets of nodes, but we're not given all the edges between the nodes. In fact, the edges are revealed one round at a time. In each round, one girl's choices are revealed. That is, the edges between that girl and the boys are revealed. Now, in each round, the algorithm has to make an irrevocable decision. And that decision is to either pair the girl with some boy, right? So we know all the edges from that girl to the boy set. So we know all the compatible boys for that girl. So we can either pair the girl with a boy. Remember, we have to pick a boy who has not already been paired because that's part of the rules of the game. If there is a boy among the girls' compatible set who has not already been paired, we can choose to pair the girl with that boy. Or we can decide to not pair the girl with any boy and move on to the next girl. But once we've made the choice, we cannot go back. We can't go back and pair the girl if we had not paired her at that point, and we cannot go back and change the pairing of that girl if we've already paired her. So the choice is irrevocable and made at that point. For an example application that is kind of along these lines and motivates in looking at this algorithm is assigning tasks to servers. Let's say we have a large number of servers of different kinds, and tasks come along, and each task can only be assigned to certain servers. Then the goal is to assign those tasks to each task to a server that can handle that task. And sometimes we may just choose to reject a task because we have an overload situation or something like that. So the online graph matching problem is in some sense similar to the problem of assigning tasks to servers. So here's an example of the online graph matching problem. We start with the set of boys, and here's the first girl A, and her choices are revealed. So in this case, A's choices, A is compatible with 1 and 4. And at this point, we have to make a choice. Either we decide to pair A with 1 or 4, or we decide not to pair A with anyone. Let's say we decide to pair A with 1, and we output 1A as our first pair. Now, the second girl node comes in, and notice that B is compatible with nodes 2 and 3, and once again we have the same choice, and let's say we choose to pair to B. Now let's say C comes in, and we have just the one edge, 1C. Now we cannot pair C with 1 because 1 is already paired with A, so our hand is forced and we don't output anything in this round. And then D comes in, and D, there's only one edge, 3D, and so we can output that edge because in this case we decide to pair 3 and D. Right, so this is an example of the online graph matching scenario. Now, what we want to do is we want to design an algorithm in this online setting that makes a choice at every step that finds as large a matching as possible by the time everything is revealed. All the edges are revealed, right? And how do we go about doing something like that? Now, it's a very complicated problem because we don't know what's going to come up. So any choice that we make at the moment might paint us into a corner. For example, because we output 1A, when C came along, we are unable to match C. Had we instead, weighted and not or output A4, then we couldn't, when C came along, we could have output 1C, but we've sort of painted ourselves into a corner and denied ourselves that choice by making an irrevocable decision along the way. So as you can see, this is a very tough problem to solve in an optimal way, and we have no hope really of finding an optimal solution or a maximum matching. What we can hope instead is to come up with some kind of heuristic that gets us, a fair distance of the way there, a heuristic that gives us a good matching, but not necessarily the best one. And such a heuristic is called the greedy heuristic. And the greedy algorithm is a very simple algorithm. And the greedy algorithm says, well, when a girl's choices are revealed, don't ever choose not to pair that girl if possible. If there is any eligible boy, if there is any boy with whom that girl is compatible, where there's an edge, and that boy is not already paired, then just pick a boy arbitrarily, pick such a boy arbitrarily, and pair that girl with that boy. And if there's no eligible boy, then don't pair girl, obviously, because we can't do anything there. So it's a very simple algorithm, the greedy algorithm. And let's say we go with this algorithm. The really interesting question is, how good is a greedy algorithm, or how bad can it be in practice? How good can it be in practice? How do we even analyze how good an algorithm is in this setting, right? To sort of analyze how good an algorithm is in the online setting, we sort of come up with a new notion that's called the competitive ratio, where we compare the greedy algorithm or any online algorithm in general to an offline algorithm. So the way we analyze online algorithms is by comparing them with the best offline algorithm. So to define this formally, suppose we have an input I. Remember, the offline algorithm sees the whole input I, and it can make an optimal choice. In this case, an optimal matching, and let's say that optimal matching is M optimal, right? Whereas the greedy algorithm sees only one input at a time, and so it ends up picking a matching that's M greedy. Now, we're going to sort of, in the most likely scenario, we know that the cardinality of M greedy is going to be less than or equal to M optimal. It can never be greater than M optimal, because M optimal is the optimal matching, and we can't do better than that. The greedy algorithm is not always going to match the optimal matching, but it's going to be less than the optimal matching, or in the best case scenario equal to it. Now, the competitive ratio of the greedy algorithm is defined to be the ratio of the cardinality of M greedy to the cardinality of M optimal over all possible inputs I. We take the minimum, right? So it's kind of the worst case performance of the greedy algorithm, right? We take the worst possible input I for the greedy algorithm, and we compute the ratio of the cardinality of the greedy output to the optimal output in that scenario. So this is what we mean by the competitive ratio of the greedy algorithm. Or in general, the competitive ratio of any online algorithm is defined in a similar manner. So let's see whether we can figure out what the competitive ratio of the greedy algorithm is. Right? Now, let's suppose the greedy algorithm doesn't actually produce the optimum matching. Now, if the greedy algorithm actually produces the optimum matching, then we know the competitive ratio is 1. But suppose the greedy algorithm doesn't produce the optimum matching, so it's actually less than the optimal matching. So here's a scenario where you can see that the optimal algorithm in this case, that's denoted in black by the black lines here, produces a matching of cardinality 4. The greedy algorithm, which is denoted by these red lines here, produces a matching of cardinality 3. And so M greedy is not equal to M opt in this case. The set of boys is on the left, and the set of girls is on the right. Now what we're going to do is we're going to consider the set of girls G that is matched in the optimal matching but is not matched in the greedy matching. Okay? So here, for example, in this case, the girl D is actually matched in the optimal matching. D is matched to boy 4, but the greedy algorithm actually doesn't match D. It matches A, B, and C, but it doesn't match D. And so the set G consists of the single node D in this case. But we define the set G to be the set of girls that are matched in the optimal algorithm, but not in the greedy algorithm. Now, we're going to define the set B to be the set of boys that are adjacent to the girls in the set G. So in this case, the set G just has a single node. The set of boys that are adjacent are 3 and 4, and so there are 2 boys in the set B that are adjacent to the girls in the set G. Now, the first observation that we make is that the cardinality of the optimal matching is less than or equal to the cardinality of the greedy matching plus the size of the set G. Now, this is by definition, because G is just a set of girls that are matched in M optimal but not in M greedy. So if you just add in the unmatched girls from M optimal to M greedy, we are going to get a match. We are going to get the size of the optimum matching, right? So the difference between the optimum matching and the greedy matching is the set of girls G, and therefore the size of the optimal matching can be no more than the size of the greedy matching plus the size of the set G. And you can see in this case, the size of the set G is 1, the size of the optimal matching is 4, the size of the greedy matching is 3, and what this is saying is that 4 is less than or equal to 3 plus 1 in this case, which is obviously true. So let's call this equation equation 1. Now, the second observation that we make is that every boy B in the set B that's adjacent to the girls in G is already matched in M greedy. Now, why must this be the case? Suppose there is a boy B adjacent to the girls in G that is not matched in the greedy matching. Now, if it's not, if there is a boy B in the set of boys that is adjacent to the girls in G that's not matched, for example, let's say boy 3 were actually not matched in the greedy algorithm, then we could just output, the greedy algorithm would have just output the 3D in this case. We would have paired that boy with that girl in G, because the rule of the greedy algorithm is if it is possible to make a match, output it. And because the greedy algorithm did not pair the girls in G with any boy at all, the only reason why that must be the case is that every boy B that was eligible to be matched with the girl in G was in fact already matched, and therefore you couldn't output that boy. And therefore it follows that every boy B that's adjacent to girls G is already matched in M greedy. So what this really means is that the cardinality of the greedy algorithm must be at least equal to B, because since each of those boys is matched, there is at least B pairs, cardinality B pairs in the greedy algorithm. So the cardinality of the greedy algorithm is greater than or equal to the set B. Let's call this equation 2. Moving on, so what do we have so far? So far, we have two equations that we derived. The first is that the M optimal is less than or equal to M greedy plus G, and the second is that M greedy is greater than or equal to B. Now let's make another observation. The optimal algorithm matches all the girls in G to boys in B, right? This is by the definition of G. We said G is a set of girls that were not matched in the greedy algorithm but were matched in the optimal algorithm, and therefore the optimal algorithm matches all these girls. And clearly they can only be matched to boys in B because that's the only set of boys that are adjacent to the girls G. Since the optimal algorithm matches all the girls in G to boys in B, it follows that the cardinality of the set G should be less than or equal to the cardinality of the set B, because otherwise we couldn't match all the girls in G to boys in B. Therefore, there should be at least as many boys in B as there are girls in G. Otherwise, we couldn't find the matching. So for example, in this case, notice that the set G has one girl, but the set B has two boys. So this equation is saying that 1 is less than or equal to 2, which is obviously true. So let's call that equation 3. Now, when you combine equations 2 and 3, equation 2 says M greedy is greater than or equal to B. Well, equation 3 says G is less than or equal to B, or in other words, B is greater than or equal to G. So when you combine equation 2 and 3, we get equation 4, which says that, well, G is less than or equal to B, but we know that B is less than or equal to M greedy, and so we have G less than or equal to B, which is less than or equal to M greedy, right? Let's call that equation 4. So far we have equation 1, which says that M optimal is less than or equal to M greedy plus G, and we just derived equation 4, which says that G is less than or equal to B, which is less than or equal to M greedy. Okay, so when we combine 1 and 4, we're just going to take 4 and substitute it in 1. We have M optimal less than or M greedy plus G, but we know that G is less than or equal to M greedy, so M opt is less than or equal to M greedy plus M greedy, which is just 2 times M greedy. So if you just take the ratio, we end up with this final equation here, which says that M greedy divided by M optimal is greater than or equal to a half. And remember, the competitive ratio is just the ratio of M greedy to M optimal in the worst case scenario. Now, we've made no assumptions at all about this scenario. So this is any scenario, and in particular, it could be the worst case scenario as well. So in the worst case scenario, the cardinality of the greedy algorithm divided by the cardinality of the optimal algorithm cannot be worse than a half. So we proved that the competitive ratio of the greedy algorithm is at least a half. Right? It could be greater than a half, but we proved that the greedy algorithm does at least half as well as the optimal algorithm. Now, this is pretty good because the greedy algorithm is a very, very simple algorithm. It doesn't even have all the information available to it. It's looking at one input at a time, and it's doing something really, really simple, yet we're able to show that it does at least half as well as the optimal algorithm. Now, we've established a lower bound on the competitive ratio of the greedy algorithm. Its competitive ratio is at least a half. Now, it turns out that we can actually create a worst case scenario with where it performs half as well as optimal. So here's an example of a simple worst case scenario. Let's say a node girl A comes in, and the compatible boys are 1 and 4, and we output 1A. Then node B comes in, and we output 2B. Then C comes in, and we are unable to output anything because 1 is already paired. D comes in, and we are unable to output anything because 2 is already paired. And so in this case, the greedy algorithm produces a matching of cardinality 2, which is 1A, 2B. But if you observe carefully, there is in fact a matching, maximum matching of cardinality 4 in this set. So for example, the optimal matching in this set would be 1C, 2D, 3B, and 4A. Now that is a matching of cardinality 4, whereas the greedy just produced a matching of cardinality 2. So in this case, the greedy has done half as well as optimal. So what we've shown is that the upper bound on the competitive ratio of the greedy algorithm is a half. Now we just showed in the prior analysis that a lower bound on the greedy algorithm's competitive ratio is a half. Since we've shown that both the upper bound and the lower bound are a half, it follows in fact that the greedy algorithm has a competitive ratio of exactly a half.